Howdy, I'd like to talk about rasterization of spheres. Here's a perfect sphere that is not composed of triangles or polygons because it's been rasterized darkly using an algorithm which I'll try to explain because I wrote a script for Evaldraw. This is a program that features a built-in code editor and compiler that can compile your code on the fly. So it's quite convenient for fast prototyping, and I've been using this program for nearly 20 years since it first appeared on Ken's website. And what do we have here? We have a editor of geometry. In this sense, we can add the spheres, add some more spheres, resize them, rotate them and about single axis. Also, they keep rotating by themselves, and the light also can be rotated this way. This is some kind of triplanar texture mapping. You can see some seams on the sphere because the texture repeats on each side of a cube, so call that is stretched on the sphere. Well, it's some simplified form of triplanar texture mapping that doesn't blend texture into each other. Let's make some more spheres, and you can see that they have correct culling, meaning that they occlude each other like it was rendered using a Z buffer, but there's no Z buffer because the algorithm being used doesn't require a Z buffer for rendering the spheres, and there's also some facility for turn around and see the construction. I told you that it doesn't use a Z buffer because this is how it's being drawn. It's being drawn by slices of a sphere that lie parallel to the viewing plane, meaning that each sphere is being split into some kind of ring-shaped sections that are stacked on top of each other to form a complete sphere. This is how opaque spheres are rendered. Also, this method shines with transparency because the transparent mode, of course, is slow in the prototype phase that in Evaldraw emulates. I'm doing an emulation of color management for blending colors into each other. It is quite slow, but you can see that despite lack of the buffer, and it makes correct rendering of transparent spheres, including the backside, and the backside is rendered separately from the front side of the sphere, like this. So all the spheres are rendered concurrently. I call this concurrent const-z rendering, and this method has been already used in my Brahma engine for rendering flat sprites, and it shows itself quite efficient for most of simple geometry. And now we I'm going to implement a sphere or other primitives being rendered this way as well. And here we have, aside from the transparent alpha composition, several shading modes. For example, the simplest way is just to fill a sphere a solid color, but you can't see any detail, and you can't even justify the Z occlusion that is being done. Other ways to fill spheres with depth data, so you can see how they are being occluded by each other. There's also option to move spheres away. This helps to, well, this can help see depth. I mean, parts being closer to the camera are lighter. Also, this also can work with transparency, but it doesn't look that nice like normals mode. The normals mode fills spheres with local normal data that are converted into texture coordinates when using the texture mode. It also helps make simple diffuse lighting. There's no fancy lighting whatsoever, like cast shadows or ambient occlusion, just some diffuse lighting without highlights like foam shading, or it's just to show the geometry. Well, so we can see that spheres are being rendered by means of simple 2D flat shapes that are essentially annuli, so-called annuli. And there are different modes to render the shapes. There's const-z mode that can do Z occlusion, but there's also a scanline mode that can't do any occlusion without using a Z buffer, so the spheres are simply plotted on top of each other in the order of their indices. Well, so the scanline mode doesn't check for depth like the const-z method that really well works really well with different cases of occlusion, like spheres being close to each other or touching each other or placed inside each other when you're working with transparency. You can place a sphere inside another sphere, and it's going to be visible. Well, so how is being rasterized exactly? We can change the pixel grid. Of course, they're using some subsampling because the algorithm can be made fast in Evaldraw environment, because it's all single threaded and going to it's all single threaded and compiled using the built-in compiler. So we just using a coarse pixel grid just to check how the algorithm is working. Well, the pixel grid, let's remove the excess of geometry just to check how it's being created on the screen. Each sphere is defined with 2 points, a center point and the control point that defines its radius and angle of rotation. So any sphere can have its position and size and orientation. There's some stray pixels because the algorithm doesn't seem to fill some poles in some cases, but let's leave it as is for now. I'll just see how it's being rendered pixel by pixel, so there is some sophisticated formula being used to make a sphere split into ring-shaped slices that they are exactly 1 pixel apart from each other, and every successive slice is regardless of the position of a sphere. It's kept 1 pixel apart from the previous sample. This helps attain decent quality yet decent speed of the algorithm, so it doesn't have to draw the same pixel over and over. We can change the hull orientation in that it's inverted, and if you're using an inverted hull mode, we are seeing the inside of the sphere inside the inside instead of the front side. We are seeing the inside, and the inside is also rendered in translucent mode. Of course we can use the translucent mode in one-sided mode, but you won't see all the fancy blending that happens when there's a two-sided mode engaged, and this makes spheres look like balloons filled with air, and the surface being diffusing light. Especially when you see it backlit like this, because this is how you can estimate the light transmission. So the annuli mode is just to test the algorithm that can fill circles. Well, there's a circle node that doesn't fill the disk, just draws the outline of the circle using a variation of Bresenham algorithm that has a subpixel precision. And I'd say that the subpixel precision is a must-have for a graphics library, because unless you want to simulate PAS1 style with wobbling vertices, and you have to support the pixel positions that don't match the pixel center or edges, and this will make circle quite irregular, but as you move it, it's being moved as smooth as possible and still being rendered with individual pixels without anti-aliasing measures. So this is how a disk is being filled. You can see that the pixels are filled if they lie inside the circle. This is the disk's mode, and you can see that this is being filled using a algorithm that inner loop doesn't even use any roots or multiplications. It's all done with simple additions and loops and branching for both the outline and disk mode. And horizontal line function is just fills a series of pixels with the selected shading mode. So the shading mode can be applied even to flat disks, and you can see the triplanar texture mapping is quite simple. Just splits a disk into sectors that are, each of them are filled using affine texture mapping. We can remove lighting so we can better see how it's done. The texture is being stretched and but there it's kept linear, so the affine texture mapping is perfect for even for spheres, as long as we are filling them with a series of flat shapes. So it's being filled not with scanline algorithm, but this with a const-z algorithm. You're perfectly fine with affine texture mapping. And if we try to use coarser sampling, for example, you step 8 pixels instead of 1 pixel, well, it will look rough and well, it doesn't look quite neat as it would look at the perfect scanline method that yields perfect quality, while the const-z is quite some it's a bit of a compromise, because you have to have a fixed step. This shows how it's being split with a constant pixel distance between each successive disk that sphere is composed of when being rendered on the screen. And the field of view thing really helps test various scenarios when your sphere is being stretched like crazy, like this. It's been it should turn into, well, the projection is an ellipse if this pole is placed in front of the viewing plane, and the sphere will turn into a hyperbola if the pole is behind the camera. So it always stays either ellipse or parabola if your pole nearest point happens to exactly lie in the plane of zero distance. So this is how the mathematics work of a perspective projection of a sphere. It makes it into a conical section. it is either an ellipse. Normally it's an ellipse, but it can be a hyperbola if the sphere is behind the camera, partially at least. Well, so we have a annular mode, and that is how it's being rasterized. Each sphere is composed from ring-shaped sections that look like this, and as long as you can fill a section and subtract a section is being subtracted on the scan line level, there's an fill disk row function, also fill ring function, that renders two circles at once and subtracts this circle from this circle on the scan line level. It is being rendered using horizontal lines, but the inner circle is not filled, it's skipped. So this is how you can render not just a sphere but any shape. You can split into sections. It can be even a Bezier spline or other types of surfaces, as long as you can fill a section of it that is parallel to the viewing plane. You can draw anything using this algorithm, and it will have a perfect z-culling. There's support for transparency, there's support for overlapping transparent shapes like this. So it's quite interesting to have this implemented in my engine. Well, you can download the script. There's Bresson solids. I'm calling this Bresson solids because the variation of Bresenham algorithm has been used to fill disks and ring-shaped annuli that are composed, and that solid objects are composed from. You can download the script, the success script, using the link in the description, and check it for yourself. Here we have keyboard controls that pretty intuitive, as long as you've been used Evaldraw, other Evaldraw scripts. So you're welcome to check this script out and send any feedback in the comments, what they think about it and what perspectives of this class of algorithms exist. And I must tell you that this is not quite compatible with shader processing. It's optimized for serial computing. Serial computing meaning that it's done on a central processor. Of course, it can be parallelized, but the parallelized to be parallelized can be used by means of tiled rendering. When you render parts of the image in separate threads, but their overall algorithm is optimized for serial computations, and it's quite the exact opposite from ray tracing or similar methods that are very readily parallelized but also they are very demanding in the terms of amount of computation, because if you are doing ray tracing, you can't reuse, well, if you're doing ray tracing using a fragment shader, you can't reuse the computations done for other pixels, because each pixel is has to be processed independently from each other, from other pixels. And here we, for the const-z algorithm, we have the amount of computation reuse. Also the scanline algorithm also reuse the computation. If we peek into the algorithm of okay, here's the slightly optimized scanline rasterizer that just traverse through lines and fills the portion that is occupied by the sphere, and there's just one square root per pixel just to acquire the distance to the camera, and the rest of the computation is divisions and multiplications, aside from the shading and other stuff that is not directly related to the sphere or rasterization. So there's also a fair amount of computation reuse. So it's a bit of two sides of different worlds of computation. So if you go for serial computation, you have a lot of opportunities to optimize your algorithms and reuse computation done for other pixels or other, but it's not quite compatible with the GPU architecture. I must tell that this is another branch of research that it's quite it's quite curious, but it should be done using other methods rather than fragment shaders or highly parallel architectures. So thank you for watching. Here's another construction I just made from these spheres. You can see that the field of view is adjusted, but the spheres, but the distance is also adjusted for the spheres to stay in the same place, and they can be moved on the plane. For simplicity, for the sake of simplicity, you can move the sphere freely in 3 dimensions. There's some neat proof of concept prototype related functions, features. So there's just a proof of concept prototype. Of course there's some room for optimization, but it's quite pointless to do in Evaldraw because it won't work fast anyway. And as soon as I make this into my Brahma engine, I'll let you know and share the process of implementation and results I get when moving this to my engine. So see you later.